The first tutorial this evening will be given by Professor and Distinguished Scientist Joseph H. Macek from the University of Tennessee and from the Oak Ridge National Laboratory. He is a well-known around the world theoretician with big contributions to the theory of three-body problem, both with analytical and numerical tools, and he will give a tutorial entitled Ion-Atom Collision Theory. Thanks.
Well, thank you very much for the kind introduction, and also to the organizing committee for inviting me to talk about really old stuff. When I was asked to give a tutorial, it occurred to me in going through the modern textbooks that you read the results of recent experiments, recent theories, but you never know, because of the way one writes textbooks, you never know the background of a lot of the relatively simple things. For example, in a single statement, one will write, well, we'll use the time-dependent Schrodinger equation. Well, this hides a lot of research that was done, especially in the 30s. But it's just an example of the sort of things that show up, especially in ion-atom collisions. Now, in a theory of atomic collisions, most of the development, most of the understanding came because of the study of electron-ion or electron-atom impact. And there was a good reason for that, because electron-atom impact was about the only kind of measurement and the only kind of process that needed modeling for example, just modeling a fluorescent light bulb. You need a lot of data from electron-ion impact and electron-atom impact. And ion-atom collisions didn't figure in very prominently. And so consequently, what we understood about atomic collisions did not really focus on ion-atom collisions. But there was one thing about ion-atom collisions that was a stumbling block for almost all treatises on atomic collisions, and that is, with ion-atom collisions, you could have charge exchange. An electron could pick up an electron from the target. Most of the theories didn't treat that. And it turns out about the period of 1955 to 1960, the physics community began to concentrate on how do you treat rearrangement collisions. The nuclear physics community had a simple picture, which is called the collision complex. The collision occurs, it's very complicated, we don't know anything about it, and then it breaks up. And when it breaks up, you could find any conceivable final state. And that was our understanding of charge exchange, which was, if you analyze it, no understanding at all. It just said, whatever happens, happens. And but the community kept looking for a way to develop ion-atom collisions so that you understood these charge transfer reactions. Those were the big question mark at about 1960. So my review starts from about 1960, which correlates with the beginning of Icpeac. Icpeac began earlier, but Icpeac played a big role in our understanding of ion-atom collisions. But prior to that, and essentially before the Second World War and during the Second World War, there was, well, essentially before the Second World War, there was a main development, which was you should use, or you could use, a time-dependent theory in which time is classical, and an example of using time as classical is time of flight. A position of a particle is given by its position vt, and v is the relative velocity, and v times t, and k dot r is mvt, h bar is set equal to 1. So the original idea was that we should use a time-dependent theory. The only problem was time doesn't fit with quantum mechanics, because quantum mechanics dealt with stationary states, and it was invented to explain the stability of stationary states. And it was only when Born recognized that with the Schrödinger equation, as opposed to Heisenberg's equations, with the Schrödinger equation, you could treat scattering states. And he, if you read Born's paper on that, you'll find that he introduced the probability distribution, the probability interpretation, in order to describe the scattering of, it turns out at that time it was electrons from a charged particle to give the Rutherford cross-section. He was the first to show that the Rutherford cross-section was compatible with quantum mechanics. But that was an important step, which wasn't recognized at the time, as usual. It was, what? K. It's classically it's h bar times r dot, which would be h bar mv, so that would be k. No, you're right. This would be v squared. That would be v squared. Yeah, it's r dot. H bar m r dot is k, and so this would be v squared. Yeah, thank you. So the idea that you could treat the continuum with the Schrödinger equation was new with Born, and Born introduced the probability distribution, the probability interpretation in order to explain it. But in that explanation, he did not describe what time was. And one of the consequences of the work in the 60s was that time was classical. it could not be a quantum quantity. You didn't have a quantum expression for time. It was purely a classical variable. Now, this is controversial even to the present day, but in the context of ion-atom collisions, it's not controversial. Time is classical. And so because time is classical, we have to be somewhat careful about how we treat it. And in order to treat it, well, let's see, I should move back and explain a little bit about time, about measuring time. Since time is classical, you needed a description that would define time, and one was time of flight. The position of a particle is some constant plus velocity times time. That was the time of flight definition of time, as you have to define a clock, and one clock that you can define is a particle moving with constant velocity. And you measure its position. That position is related to time by r equals vt. Now, this was not particularly significant at that time, but with the introduction of beam foil collisions, where you shot ions through a foil and measured the emission of photons as a function of the position afterwards, you interpreted it as a function of time afterwards. So time was measured by this time of flight, and that defined the clock. So you defined a clock, and that was important. Once you defined the clock, that was something you could then use with ion-atom collisions and say, well, you know, we can let's see, we can factor out the time dependent. We can factor out the motion of the relative motion by just e to the I k dot r, and then we're left with this. And this is the electronic motion that we don't know, in principle, we don't know anything about. And then we substitute this in the Schrödinger equation. Make this approximation. This is a critical approximation, that this is I d psi by dt. This is going from relative motion to I d psi by dt, and we get the time-dependent Schrödinger equation, where h is the kinetic energy plus the v, there should be a psi here. This would be t psi divided by psi. So this was the way one introduced time. Now, the question is, why is this important? In the, you're reading about it in the textbook, you just make one statement and you go to the next, but why is it important that we're using a time-dependent theory? And the reason is that when we use the time-dependent Schrödinger equation, we're replacing this operator by I d by dt. In effect, we're replacing a operator operating on the relative coordinates by I d by dt. And this, of course, if you look at it, how it operates on a product function, you can see that it's a two-electron operator. It causes transitions of one or two electrons because of the fact that when you expand it out, you get this transition here in the space of u, and this transition in the space of v. But when you use the time-dependent Schrödinger equation, Sorry, I've made a mistake here. This becomes just, I'm sorry, this is all wrong. This should become u dot v plus u v dot. That's the derivative with respect to t. And so that's one electron operator. So we have a one electron operator. This is an error. And the use of a one electron operator allows us to use the Wigner-Eckhart theorem. This t means d by dt. That if you operate with the d by dt, you operate only on one of the electron operators, not both. They cancel out. So the replacement of del squared r, the real kinetic energy, with the time-dependent version, which is d by dt, changes your whole theory from one where the one electron transitions are dominant. There are no two electron transitions unless they are two one electron transitions. That is to say, you first transition on one and you transition on a second. And so that's the important thing that that came out of that work, which was that you could use a classical trajectory. So that was the first real advance. The next advance came much later when one was studying electron capture and proton-hydrogen collisions. Now, theory had a whole bunch of formulas for this. But experiment showed, and it was just the right experiments, the experiments by Lockwood and Everhart showed that in an ion-atom collision, the charge cloud oscillates. The charge cloud oscillates between being on the target or the projectile, and there's a frequency which is easily calculated, and this was observed experimentally by Lockwood and Everhart, who studied protons on hydrogen going to hydrogen plus protons, in other words, electron charge exchange. And they were able to do the coincidence measurements that enabled them to measure this process. And they showed the electron capture as a function of the reciprocal velocity. Reciprocal velocity is essentially time. 1 over v was time. So they found that the transfer oscillated as a function of time, as given by this picture where the charge cloud oscillates between two separate states. And the two separate states that depends on the procedure, on the experimental situation. In this case, it's protons on hydrogen, and the two separate states are a hydrogenic state on an atom and a hydrogenic state on the target, and they oscillate back and forth. The electron distribution just oscillates. And depending upon whether it breaks up with when it's on one or the other, you get electron transfer. So this was the first indication that this procedure of taking the hydrogenic states, the adiabatic hydrogenic states, and projecting the charge cloud onto coordinate space, and that projection oscillate back and forth between target and projectile, and they were actually able to measure that. So that was the first indication that that picture was correct. Now, technically, you will find in the literature that this is said, oh, that's the perturbed stationary state method. Perturbed stationary state being this state. But because of the developments of scattering theory, there was the belief that the perturbed stationary state method was incorrect. It couldn't possibly be correct because of the fact that it treated transitions as if there was no motion whatsoever of the particles. That's the perturbed stationary state. Well, it turns out that view dominated the theory for a long time, but it was eventually found that it was correct. It was correct to treat these as stationary states. And it was only with the use of the so-called advanced adiabatic theory of Soloviev, who showed how to make the perturbed stationary state theory rigorous. And so it became rigorously true with his developments. And in the tutorials, we'll go to Soloviev's transformation, which turns out to be needed in order to treat these processes. So at any rate, that was the accomplishments up until Lockwood and Everhart, but they went further than that. And so they, as the experimentalists are often wont to do, they measured further systems. And they found the data that led to the so-called Fano-Lichten model. Now, the Fano-Lichten model was a model for ion-atom collisions, which essentially dominated the topics in Icpeac from about 1950 to 1980, somewhere in there. The Fano-Lichten model, it was the probing of the predictions of the Fano-Lichten model, played an enormous role in the development of Icpeac. Since then, of course, the community has moved on. The Fano-Lichten model is well understood. We know what it is, and the community has moved on to, other things. But the Fano-Lichten model was based on this picture, which is really essentially here. The charge cloud oscillation was the mechanism by which electrons were transferred. And it was found that with this model, and it just so happens that I was working with Professor Fano at the time the model was being developed. Of course, I was completely in the dark. I had no idea why there were so much excitement about the model, but I'll explain that a little bit later. But there was a lot of excitement about the model, and the main consequence of the model was that you would you would predict that there were these multiply excited argon states, which then autoionized and emitted a fast electron, one or more fast electrons. And these fast electrons, now I've neglected to put the other argon here because that's neither here nor there, it's not relevant. But observations by M.E. Rudd at that time at Concordia confirmed that there were these states with multiple electrons excited. And they confirmed it by observing the electrons that were emitted. So that was an important step, and that led to a great development in ion-atom collisions, which is recorded in the proceedings of Icpeac between about 1973 and 1985 or so. About that period is dominated by studies of the Fano-Lichten model. But the question is, why is this important? Why was it important that you saw these multiple excitations? Now, at that time, I was a postdoc with Ugo Fano, working on a totally different problem, but I couldn't help but overhear the discussion about the Fano-Lichten model and all the excitement about the Fano-Lichten model. So I asked Professor Fano, not knowing that this was not a good thing to do, but I asked Professor Fano, what's so important about the Fano-Lichten model? I mean, that's a logical question to ask if you're a green PhD, as I was, a beginning postdoc. I said, what's so important about it? And I thought he would bite my head off, but he didn't. He appreciated the question because it gave him a chance to explain what was so important about the Fano-Lichten model. And he said, well, the model shows how ion-atom collisions can produce unusual states of atoms that cannot be produced by other means. And that was true at the time. That was about 1971. There was no other means of producing these states that were being observed. And these states that were being observed were states where many electrons were excited. Not just one or two, as you get with electron impact or with photon impact, but with ion impact. So that was that essentially satisfied my curiosity. But later on, I realized that there was another reason that the Fano-Lichten model was important, and this was when I tried to make some calculations related to the Fano-Lichten model. And that was that this model told us how to use the independent electron model. At that time, computers were not so big. The best you could do was to treat independent electrons, Hartree-Fock level of approximation. Treat independent electrons. And so this model told you how to treat independent electrons. And the model gave a prescription that wasn't really immediately obvious at the time. You would think, well, if you're doing independent electron, you just use the Hartree-Fock ansatz. You make the Hartree-Fock approximation. But the model showed that, well, you should use H2 plus type orbitals with variable screening. That's not Hartree-Fock orbitals, but those are H2 plus orbitals with variable screening. Now, of course, the nice thing about saying variable screening, it's not defined. And so, since it's not defined, it can be anything you want it to be. But it turns out that Eichler and Villa gave a definition of the H2 plus type based on a Thomas Fermi description of the electron distribution. They gave a Thomas Fermi electron distribution that essentially told what the variable screening was. And their results completed the somewhat inexact definition of Fano-Lichten. But there was some additional insights needed because you were dealing with many electrons, not just one. You needed some insights from John Redding to implement multi-electron distributions based on an independent electron model. He gave a general theory of wave functions, antisymmetric wave functions, where you're using an independent electron model, which is time dependent, so it changes, and so the transition rates depend upon your antisymmetrization. And this was work by John Redding. Okay. And now, in the same period, it was the understanding of electron capture had reached a fairly significant point. We sort of understood it, but simultaneously there was another aspect of electron capture which was being studied, and that was what states are electrons captured to? You know, it's just simple energy issue. Electrons could be captured to the ground state, to the first excited state, to the next excited state, and so on. But then the so on would have to eventually end somewhere. And interestingly enough, it just so happens, after I had finished my work with Professor Fano, I was working with Ian Cheshire at Atomic Energy Research Establishment in Harwell, who was doing some very precise calculations of electron capture. And he was using some very elaborate but standard methods. And I asked him, well, what happens when n goes to infinity? What happens when the electrons are captured not to a bound state, but n goes to infinity? What happens then? He says, well, they just don't, the cross-section goes to zero. Nothing happens. Well, it turns out he was wrong, because what happens is the electrons go to continuum states of the projectile, and that process is known as electron capture to continuum states. It's just another name for the process as n goes to infinity. So with that, the community had certainly, in the low energy limit, had a fairly good picture of electron capture. And electron capture was an important part, was really the main difference between collisions, ion-atom collisions, and just electron-atom collisions. But there was also the high energy limit, and this was always a problem, because in all of these processes, in trying to understand them, you build a classical model, and there was no classical model for capture at very high relative velocity until Thomas said, oh, well, there is a model. Thomas, the same Thomas of, this is the Thomas of, well, we know him as the Thomas of the Thomas collision mechanism. He said that capture occurred by an ion hitting an electron, the electron bouncing off the target, then recaptured. That was the double collision mechanism. And he calculated it classically, and the results he got didn't agree with any experiments, but that was not important. But somewhat later, actually quite a bit later, Joachim in Belgium took this model and calculated the mechanism purely on the basis of quantum mechanics, using plane waves for the motion of the fast electrons. And he did this. And he did it essentially exactly. The only trouble was, first of all, it did not show any double collision features until the ion collision reached 50 MeV. That's very high energy. That's much higher than we had expected. That was one of the problems. But the other problem was that his quantitative calculations got a cross-section was way too big. And this was general feature of charge transfer studies at that time. The physicists would come up with a very clear physical picture based on classical mechanics, which was, and these were reasonable physical pictures. And then you would translate those pictures into the quantum theory, and translating them into the quantum theory meant replacing trajectories by plane waves. That was how you translated them. They would translate them into the quantum theory and then make the calculation in the quantum theory, and the results were way too large, very, very large. Didn't agree at all. So that was a big divergence between theory and experiment. Although we now understand in retrospect that the classical models on which they were based were probably fairly realistic. But the use of plane waves was not legitimate. So it wasn't until fairly late in the game, actually this was in the 80s, John Briggs recognized that if you replace the plane waves by Coulomb waves, you just made this simple replacement of plane waves by distorted waves everywhere, then two things resulted. The effects of the double collision show up at 5 MeV rather than 50 MeV. And the effects basically were a enhancement of the cross-section. So this shifted attention from 50 MeV down to 5 MeV, where it turns out experiment did find this enhancement. The other thing was that by that replacement, the magnitudes of the cross-sections are physically realistic. What I mean by that, and what we mean by that, in the books you see this very often, but you don't know what it means. What it means is, well, you know, in collision theory, you all know, you've all heard of unitarity, you know, probability can't exceed 1. That's the unitarity limit, you know, probability exceeds 1. And when we say physically realistic, we mean we got cross-sections such that the probability on which they were based never exceeded 1. So they were physically realistic. That's what that means. But that was an important step. That was an important step because it told us how to do the high energy collisions. And so in the end, we were then searching for, once we once the community had this understanding of how ion atom collisions work at low energy and how they work at high energy, or at least partly how they work at low energy and how they work at high energy, but the main part was understood, we wanted a comprehensive theory. We didn't have a comprehensive theory. It went from perturbed stationary state at low energy to multiple Born approximation at high energy, and this is not a very, you don't see how one connects with another, but you could make a connection in the following way. One is you take the Fourier transform of the target wave function, psi of k. That's the target wave function. And that gives you a velocity distribution of electrons around the target. And now you just forget that the target is there, or at least almost forget the target is there. You just have a collision of a moving projectile with a velocity distribution of electrons. And that, of course, is simple enough for us to treat. And so it's simple enough for us to treat, so we do that. And in the projectile frame, we transform from the lab frame to the projectile frame. And in the projectile frame, you just ask, what's the probability for certain free bound transitions? And people have been making calculations of free bound transitions for several years, from the beginnings of the 30s. But they were making them for free bound transitions subject to electromagnetic interaction. In this case, you had free bound transitions, but the transition operator was the recoil of the remaining target that you'd left out. But we knew how to treat that. So by treating it as a free bound transition, you had a comprehensive picture of ion atom collisions. So that's where we ended up. Let's see. At the present time. And in the tutorials, I will have some tutorial problems prepared. One is let's see. Is this treatment of electron capture by a charge cloud oscillation? That's how we understand charge transfer. And you can make simple calculations of that. And then the other, so we'll start with how you put the time into the Schrodinger equation. And then we'll conclude with, well, if we have enough time, we'll conclude with using this time-dependent, okay, thank you. I'll finish up. I'm being told that it's time to quit, and that's fine with me. Oh, okay, 10 minutes. Anyway, so the first step was, and it's the most important one, but you never see it in the quantum mechanics books, is how do you put time into the Schrodinger equation? Because time is a classical variable. It's not a quantum variable. And yet you must put time into the Schrodinger equation. Now, we know how to do it, and as a matter of fact, if you go back to an old text on quantum mechanics, it's by Kemble. At that time he was at Harvard. He wrote a text on non-relativistic quantum mechanics in let me try to think. It was 1933, I believe, somewhere in that period. And in that text, he has a long discussion of the time dependence in the Schrodinger equation. It's a discussion we never ever put in the quantum mechanics text anymore. We just understand that it's there. But it turns out that is important for ion atom collisions owing to replacing a 2-electron operator by a 1-electron operator. That's why it's important. It's particularly important for ion atom collisions. Okay, well, thank you very much. Guess I'll see you in a few minutes for the first of the tutorials.